Welcome to the second part of the discussion about Taylor series. Recall that in a remark in the previous video, it says that a function may not always be equal to its Taylor series at all points in the interval of convergence of the series. So here, in this video, we answer the question, when is a function equal to the sum of its Taylor series? Now, if a function is equal to its Taylor series, then we can approximate function values using partial sums of the Taylor series. We can also determine the accuracy of these approximations. So these are the two goals for this discussion. So let's now consider the following definition. So here, let f be a function whose first k derivatives exist at a. We define the kth degree Taylor polynomial of f about a, denoted by p sub k, to be the polynomial defined as follows. Notice that this Taylor polynomial of f are the first k plus 1 terms of the Taylor series for f. We also define the remainder to be the function r sub k, given by the difference between the Taylor polynomial p sub k and the function f of x. This is the expanded form of the kth degree Taylor polynomial of f about a. Notice that the terms of p sub k are the first k plus 1 terms of the Taylor series of f of x about a. So here we say that a Taylor polynomial of f is a partial sum of the Taylor series for f. And so we can say that the Taylor series on the left-hand side of this equation is just equal to the limit of the Taylor polynomial p sub k as k goes to positive infinity. So this leads us to the following theorem. Suppose that f is a function whose derivatives of all orders exist at a. And then let's denote the kth degree Taylor polynomial of f about a by p sub k of x. Then f of x is equal to its Taylor series about a if and only if the limit of the remainder r sub k is 0 as k approaches positive infinity. So this theorem answers the question, when is a function equal to the sum of its Taylor series? From the previous theorem, we learned that a function is equal to its Taylor series if we can show that the limit of the remainder r sub k is 0. However, in practice, it is often useful to have an estimate for the remainder rather than having an exact value for it. Taylor's inequality allows us to estimate the remainder term appearing in the Taylor approximation. Let's now go through Taylor's inequality. So Taylor's inequality states that if the magnitude of the k plus first order derivative of f is less than or equal to some number m for some values of x in the interval a minus d, a plus d, okay, then the remainder function r sub k satisfies the following inequality. Okay, so let's go through this one by one. Recall that r sub k is the remainder function. By definition, this is equal to the function f of x minus the kth degree Taylor polynomial p sub k of x. Okay, so f here is the actual value of the function or the thing that you want to approximate, and p sub k here is the Taylor polynomial, which is your approximation. So you want r sub k to be small. For r sub k to be small, its magnitude must be bounded by a small number, okay, which is this quantity. So you want this to be small. How can you make this small? So you want the numerator to become small, which is the number m. Now, how do you compute m? So you compute the magnitude of the k plus first derivative of f of x. So m is the bound in this magnitude. Okay? And then you can also make this quantity small by making the denominator large. So you can make the denominator large by increasing the number of terms in the Taylor polynomial. So note that k here is the degree of the Taylor polynomial. Okay? And this is the thing that you can change, or this is the thing that you can choose. Okay? So the degree of the Taylor polynomial. Okay, next, let's look at the absolute value of x minus a. So x here is the point where you want to evaluate f of x. On the other hand, a is the point where the Taylor polynomial is expanded. That is, this is the point where you are taking the derivatives. And d here must be small so that x and a will be very, very close to each other. Okay? So that is what Taylor's inequality states. Okay, so a useful fact. So here, let a be a real number. So you can show by absolute test for a ratio test for absolute convergence that this expression or this power series absolutely converges for any real number x. So if this power series absolutely converges, then these limits are 0. Okay, so these limits are 0. So equivalently, we have the following limits. Okay, so this is the limit that we want. Okay, this part. Because if we can show that the limit of this expression is 0, then this expression goes to 0. Okay? And if the limit of this is 0, and since the magnitude of r sub k, it's inside the absolute value, so this is non-negative, then by squeeze theorem, r sub k must be, or the limit of r sub k must be 0. Okay, so I hope everything is clear now. Let's have an example. In this example, we want to show that sine x is equal to its Maclaurin series for all real number x. Then for a follow-up question, we want to find the Maclaurin series for cosine x. So in number 1, what we need to show is that the limit of the remainder function r sub k is equal to 0. Okay, so to start, let f of x be equal to sine x. So note that the k plus first derivative of f is either plus minus cosine x or plus minus sine x. And being circular functions, they are bounded by -1 and +1 on either side. Okay, and so the magnitude of f k plus 1 of x is less than or equal to 1. And this is for all real number x. Okay, and so by Taylor's inequality with m equals 1, so from here, okay, we obtained m, we obtained this expression. Okay, so the magnitude of r sub k is less than or equal to 1, which is the bound for the magnitude of fk plus 1, over k plus 1 factorial times the absolute value of x minus 0 raised to k plus 1. So here, a is 0 because we are dealing with a Maclaurin series, okay, where we take the derivatives at 0. So we have this expression. Okay, and if you can recall, from the useful fact, the limit of the right-hand side of the inequality is 0. So if the limit of this is 0, then by squeeze theorem, the limit of the absolute value of r sub k is also equal to 0. And so the limit of the remainder function as k approaches infinity is 0. Okay, so we're done with number 1. So we have shown that sine x is equal to its Maclaurin series for any real number x. From the result in number 1, we have shown that for all real number x, sine x is equal to its Maclaurin series, which appears in the right-hand side of this equation. Okay, so from this result, let us now find the Maclaurin series for cosine x. So note that cosine x is the derivative of sine x. So therefore, we can differentiate both sides of this equation to find the Maclaurin series for cosine x. So differentiating the right-hand side, we get the summation from n equals 0 to positive infinity of negative 1 to the n, and then we bring down the exponent for x, so that's 2n plus 1 times x raised to 2n over 2n plus 1 factorial. So we can cancel out the common factor 2n plus 1, okay, and this gives us the summation from n equals 0 to infinity of negative 1 to the n, okay, x to the n over 2n factorial. And this is for all real number x. So recall that when differentiating a power series, we move the index one step forward. But in this case, we start at 0 so that we can incorporate the first term of the Maclaurin series for cosine x. So note that when n is 0, this is equal to 1. Okay, so the first term of this is 1, which is actually f0 of 0. Right? So f0 of x is the function itself, which is cosine x. So evaluated at 0, okay, so this is the first term. Okay, we have cosine 0, which is equal to 1. Okay, so we have now found the Maclaurin series of cosine x by differentiating the Maclaurin series of sine x. Okay, just a recap. So recall that we have two goals for this discussion. The first goal is to determine when a function is equal to its Taylor series, and we have learned that a function is equal to its Taylor series if we can show that the limit of the remainder function r sub k is equal to 0. Now, for our next goal, we want to approximate function values using Taylor polynomials. Okay, so let's first have some recall. Okay, consider a differentiable function f on an interval containing the number a. Then, for x in the interval, f of x is approximately equal to f of a plus f prime of a times x minus a. Note that the expression on the right-hand side is the equation of a line that is tangent to the graph of f of x at the point a. So this expression on the right-hand side is called the linear approximation of f at a. So here we are approximating the function f of x by some linear function as follows. Okay, so now let's consider the following remark. Okay, so this is why we need to know when a function is equal to its Taylor series. Because if a function is equal to its Taylor series about a, we can use a Taylor polynomial to approximate the function f. So for k in n, or in the set of natural numbers, f of x can be approximated by the kth-order Taylor polynomial p sub k, which is equal to the following summation, or the following polynomial. So let's have an example. So use the Maclaurin polynomial of degree 7 for sine x to estimate sine 1 and sine 2. In each case, determine the number of decimal places to which the approximation is correct. So this example tells us two things. Number one, we can use Maclaurin polynomial to estimate the values of sine 1 and sine 2. So we know that sine 1 and sine 2 are not easy to compute because 1 and 2 are not special values for the sine function. Okay? And then number 2, it tells us that we can use Taylor polynomials to determine how accurate our approximation is. The Maclaurin polynomial of degree 7 for sine x is given by p sub 7 of x, which is equal to the summation from n equals 0 to 3 of negative 1 to the n over 2n plus 1 factorial times x raised to 2n plus 1. Note that we stop at n equals 3 in the summation because when n equals 3, the degree of x is already equal to 7, which is what we want. Okay, so expanding this, we get x when n equals 0, negative x cubed over 3 factorial when n equals 1, x to the 5th over 5 factorial when n equals 2, and negative x to the 7th over 7 factorial when n equals 3. So notice that we only have 4 terms for the Maclaurin polynomial of degree 7 for sine x. Okay, so let's now go to the derivative of sine x. So note that the k plus first derivative of sine x is either plus minus cosine x or plus minus sine x, which are all bounded by negative 1 and 1. And so the magnitude of this derivative is less than or equal to 1 for any k. Okay? And so by Taylor's inequality, we have the magnitude of the remainder function r sub 7 of x is less than or equal to x to the 8 over 8 factorial. So we now have the expressions for p sub 7 of x and the magnitude of r sub 7 of x. So let's now go to estimating the value of sine 1. So for x equals 1, sine 1 is approximately equal to the 7th order or 7th degree Maclaurin polynomial e sub 7 of 1. And this is equal to 1 minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial. So you can verify that this is equal to 4,241 over 5,040. So in decimal form, this is approximately equal to 0.841468254. So on your own, you can verify using your calculator the value of sine 1 and the decimal value of this rational expression. Okay, and you can see how close or how far away these two values are. Now, to check the accuracy of our approximation, we can now use Taylor's inequality as follows. Okay, so for the correctness, we evaluate r sub 7 at x equals 1. So when x is 1, the magnitude of this remainder is not greater than 1 over 8 factorial, which is approximately equal to 0.000025. So this means that the approximation is accurate to at least 4 decimal places, or the number of zeros on the right of the decimal point. Similarly, for sine 2, this can be approximated by the Taylor or the Maclaurin polynomial p sub 7 of 2, which is equal to 2 minus 2 cubed over 3 factorial plus 2 to the 5 over 5 factorial minus 2 to the 7 over 7 factorial. And this is equal to the fraction 286 over 315, which is approximately equal to the following decimal value. Okay, so to check the correctness or the accuracy of this approximation, so let's have r sub 7 of 2. So the magnitude of this is less than or equal to 2 to the 8 over 8 factorial, which is approximately equal to 0.006. So there are 2 zeros on the right side of the decimal point, directly to the right side of the decimal point. So we say that the approximation is accurate to at least 2 decimal places. We are now in the last example for this lecture video. Here we want to find the second degree Taylor polynomial for f of x equals square root of 2x about 2 and use this result to approximate the numerical value of square root of 4.2. For the solution, given that f of x equals square root of 2x, we then evaluate this at x equals 2, since we want to expand the Taylor polynomial about the number 2. Okay, so we have f of 2 equals 2, or square root of 4. Okay? And so we have c sub 0, which is the coefficient for the first term, to be equal to 2 over 0 factorial, or 2. Okay? Next, we consider the derivatives of f of x. For f prime of x, this is equal to 1 over square root of 2x. Now, f prime of 2 is equal to 1 half. And so, c sub 1 is equal to 1 half in the numerator and 1 factorial in the denominator, which gives us 1 half. Lastly, f double prime of x equals negative 1 over the quantity 2x raised to 3 halves. Evaluating this at x equals 2, we get f double prime of 2 equals negative 1 over 8. And so, c sub 2, which is our third coefficient, is equal to negative 1 over 8 in the numerator and 2 factorial in the denominator, which gives us negative 1 over 16. Therefore, the second degree Taylor polynomial for f about 2 is given by p sub 2 of x, which is equal to 2 plus 1 half times x minus 2 minus 1 over 16 x minus 2 squared. Okay, so this is now the second degree Taylor polynomial for f about 2. Okay, so this is of degree 2. And so, to approximate the numerical value of square root of 4.2, we have f of 2.1. Okay, so notice that if x is 2.1, then we have square root of 4.2. Okay? And we want to approximate this using p sub 2 of x. So we write approximately equal to p sub 2 of 2.1. So we just plug in 2.1 in this polynomial. And so p sub 2 of 2.1 is equal to 2 plus 1 half times 2.1 minus 2 minus 1 over 16 times 2.1 minus 2 squared. So computing this, you will get 3279 over 1600. So this is now the approximation for the square root of 4.2 using the second degree Taylor polynomial for f about 2. Here are the plots of the functions p sub 2 of x and f of x in the previous example. Again, p sub 2 of x is the second degree Taylor polynomial of f of x about 2. P sub 2 of x is of degree 2, whose second degree term has a negative coefficient. That's why the plot for p sub 2 of x is this red plot that is a parabola opening downwards. The blue plot here is the plot for f of x equals square root of 2x. Note that at x equals 2, the plots of the two functions almost coincide. So this is why p sub 2 of x could be a very good choice to approximate f of x for values of x very close to x equals 2. Here are some exercises about approximation using Taylor and Maclaurin polynomials. This ends my discussion about Taylor and Maclaurin series. Thank you for listening.